Welcome, and thank you for standing by. At this time, all participants have been placed on a listen-only mode for the duration of today's conference. This call is being recorded. If you have any objections, please disconnect at this time. I would now like to turn the conference over to Michelle Resnick. You may begin.
Thank you, Wendy. My name is Michelle Resnick, and I'd like to welcome you to today's webinar titled Energy Goal-Based Building Procurement, Achieving 90% Energy Savings in the Parking Structure. This webinar is presented by the Building Technologies Program at the U.S. Department of Energy. We're excited to have with us today the experts that guided the space procurement process used to design and construct NREL's new 1,800 space parking structure. But before we start, I have some housekeeping items to cover. First, as Wendy mentioned, everyone today is in listen-only mode. We will have a Q&A session at the end of the presentation. You can submit your questions throughout the webinar using the live meeting window. To submit a question, click on the Q&A link on the top bar of your screen, type the question in the box, and click Ask. Please be sure to click Ask and not the symbol of the raised hand. Our speakers will address as many of the questions submitted throughout the webinar as time allows after the presentation. Today's speakers are Jennifer Scheib, Shanti Pless, and Bill Macey. Jennifer and Shanti work at NREL and focus mainly on applied research and design processes for commercial building energy efficiency and building integrated renewable energy projects. Bill Macey was on the design and construction teams for the inception of the parking garage process and has also worked with the team on other NREL net zero energy projects. They will provide a summary today of how they achieved 90% energy savings in this parking structure, including specific solutions such as LED lighting that they employed, and they will also review some preliminary energy performance results. And with that, I will go ahead and turn the presentation over to Jennifer. Or maybe to Shanti.
Great, welcome all. So we're going to go through some background here. Uh-oh. Hold on a moment. We're going to get the slides going. Okay, so here's what we're here to talk about, give you some background why we built a 1,800-car parking garage on our campus, talk about the details of the structure from the design build performance objectives through the design solution and the energy performance, and talk about how a parking garage can to leverage innovation in the industry and resources for replication. So this is what our sleepy little NREL campus looked like in Golden, Colorado before 2007. It was mostly PV research laboratories and advanced biofuels research laboratories. We have a significant amount of our staff were in leased office spaces off of our campus, half a mile away or so. And so there was a big disconnect between the employees and the support staff and human resources, executive management and such, from the core mission of NREL and the laboratories. And so there's a big push to move as many of our staff onto our Department of Energy-owned campus out of leased office space. And so this is what it required a significant investment in our campus, and that has been happening since 2007. Since 2007, we've built offices for over 1,300 employees. Additional laboratories with another 200 workstations, a significant growth in our data centers and supercomputers, as well as a cafeteria, new site entrance buildings, and a significant campus infrastructure enhancements. And so that work has been happening since 2007. And this is what our campus looks like now. You see the parking garage there in this photo, and we'll be talking about that. But in general, there's a lot of additional facilities and employees on this campus, and you can see this is about the extent of the campus with limited parking. And I believe everyone can see my pointer here. Nope, maybe not. So in the upper left of that picture, you can see a surface parking lot, and the initial intent was to have all surface parking, but then quickly realized that we could fit over, we have over 2,000 employees here in NREL and not enough parking for everyone to come to work. So there is a significant effort among NREL to incentivize alternative transportation methods such as carpooling and ride shares and biking to work. There's an amazing amount of people that bike to work. as well as public transportation with buses and light rails coming nearby as well. And so even with all that alternative transportation methods, and NREL staff are great at utilizing that, there was still a need for a parking structure to handle everyone else that does drive. And so that was the need. And so on some of the details of the procurement process, and so before 2007, we built a few additional labs using the typical design, bid, build, delivery process, and we had significant lead goals, and so it was somewhat of a difficult process to make sure energy efficiency was incorporated, and it always ended up costing a fair amount extra because there's always extra efficiency added in. And so since then, we've realized that we can build projects quicker and faster using a streamlined design build process, project delivery process. And we started developing that process after 2007. The first project was our research support facility, the RSF. And what was different about this process is that it is what we call an energy performance-based design build process, where energy use requirements are specifically incorporated into the design build contract and the RFP selection process. For example, the RSF, an office building had an energy use intensity requirement of 25,000 BTUs per square foot per year in the contract. And other ways we've done this with our smaller buildings, like a site entrance building, SEB there, was to say net zero energy in the contract. And so we've learned how to apply energy performance requirements in our performance-based design build contracts on multiple projects since 2007. And we'll be talking a lot more detail about how that applies to a parking garage. But that does incorporate in general things like energy modeling to substantiate goals, metering to verify that those goals are actually being met, in a robust incentive program so that owners can have some hope that their design-based energy goals can be actually met in operations. And so we'll be talking about how that applies to a parking garage specifically in this webinar. So I do want to point out that in our research group here at NREL, we do have an active DOE project to document this process and to develop how-to guidance for other owners looking to incorporate energy use requirements into their contracts and performance or procurement contracts for new construction projects. And so this webinar is part of that effort. And so you'll look for that and additional resources at the end of the webinar and how to get access to that. So with that, I introduce Jen Scheib to talk about the details of the garage.
Thanks, Shanti. So for the remainder of the webinar, we're going to tell the story of how DOE and NREL procured the best-in-class parking structure that uses 90% energy, less energy than an ASHRAE 2007 baseline. And along the way, we're going to give some general guidance on how the process can be replicated. Shanti showed the need for parking on the NREL campus and that it needed to be a structure versus a lot due to space constraints. And I don't know if you could tell from the campus plan, but the site slopes up towards the other structures on campus. And so it was possible that the structure would be buried into the hill using a lot of electric lighting or ventilation. And so we needed a way to simultaneously control cost and energy use. And so that's really why we decided to use the performance-based procurement process for a structure, a simple structure that we had used for offices, the lab, and the cafe. So the key components of the procurement process that NREL and DOE agreed upon to start the project was a $29.8 million lump sum for the structure and a small entrance building. To use a best value selection approach, which I'll talk a little bit more about later, and a $1 million award fee for superior performance. And as Shanti said, that's really to incentivize the design build team to go above and beyond in achieving the aggressive project goals. So at project initiation in April, or slightly thereafter, in November of 2009, the first task for NREL and DOE was to form an integrated project team. So an IPT is really an owner's representative panel of experts for different facets of the project, for contracts, environmental health and safety, energy. And as a little background, Shanti and I, who are in the commercial buildings group at NREL, are talking about the garage because we sat in on the IPTs along with Paul Torsolini and other NREL DOE folks on different campus projects. So the primary task for the IPT is to help develop the goals and draft the request for proposal, or the RFP, to review proposals that come in, and to review substantiation documents such as the energy modeling report to confirm that the RFP goals are being met in design and construction. In 2009, we started drafting the RFP, and at that time, the request for qualifications, or the RFQ, was released. We narrowed down the RFQ responses to the 3 most qualified teams, and then those 3 teams received the RFP with the energy goal. And that 2-step phase is really important because it gives the proposing teams a 1 in 3 chance of getting the project, which makes that upfront design effort required to show that how you're going to meet the goals worth it when you have a better chance. So another key step is to have team interviews. And let's see, that happened in July of 2010. And that gives the team a chance, or the proposing teams a chance to ask the owner questions about their assumptions, the goals, and really gets everyone on the same page. So for the NREL parking structure, the Hazelden RNL design build team was selected. They clearly showed how the project goals written in the RFP would be met in their proposal. And they did really a lot of the critical thinking up front. So when kickoff happened in fall of 2010, they were well on their way to meeting substantial completion, which happened in early 2012. So, let's see. Sorry about that.
Ready to go now?
Okay. So what was written in the RFP that they were responding to? The next few slides give actual contract language, and the way that NREL has done it on other projects and on the parking structure is to split up the language into 3 tiers. So there's a mission critical tier, this is the top one that I'm showing now, and these are really the project goals, the high-level project goals that NREL and DOE agreed upon when the money was given. Then there's a highly desirable and an if possible tier. And this is where the best value comes in, because everyone's required to meet the mission critical goals, but the proposing teams can agree to or propose to meet different parts of the other tiers. And so NREL selected the team that offered the best value, or the most, the best value for the money.
Or the most scope is another way to think about it.
Yeah,
the most scope for firm fixed price contract.
Right.
The critical thing to share with the audience, this is Phil Macey, is that what this does, if you're thinking about this from a contract basis, the cost of the project is fixed. So the competition isn't about the lowest price. The competition is about providing the owner with the best value for the same amount of money. That's a very different level of competition, and really puts the emphasis from the beginning on value. You don't value engineer later. You don't create value later. Ownership gets value created at the time of proposal.
Right. And just a side note here, this parking structure maximize lead points. Parking structures, as you probably know, can't be LEED certified, so this was part of the sustainability effort and just to guarantee a minimum level of energy performance. So the highly desirable goals are really where we went above and beyond and said, okay, we don't want just a typical parking structure. We want a gateway to our campus. It offers different, entry point for different forms of transportation, and we want really aggressive energy savings. And so some of the highlights here are to achieve an energy goal, specific energy goal of 175 kBtu per parking space per year. We've learned on our past campus projects that it's really important to be specific about the goal and not, a percent saving is okay, but the more specific the better because it's easier to show substantiation and to measure and verify later. Maximize PV capacity, give electric vehicle charging spaces, and then the mission critical tier just goes a little bit further and says, sorry, I went backwards. If possible tier, goes a little bit further and says, okay, let's provide more capacity, motorcycle parking, so not really critical items.
If I could, Jen, this is Phil, second time. What you're looking at is a very disciplined approach to asking what you want. What you've just seen in the last 3 slides are actually rank ordered. Each of those items had some representation, some audience, if you will, that wanted that particular item as a part of the project. And the group organizing the RFP exercised a lot of effort on the part of ownership to put in order all the things they wanted, write them all down, and commit to them, and then stay committed to them all the way through the project. It's a challenge. The benefit is, as an ownership group, you have real clarity when you enter the project, and you can really drive the value in the equation when you write an RFP this way.
Okay, so we're going to talk now a little bit about how NREL determined the energy goal. So we didn't really have data from other garages or an example of a best-in-class structure that we could use to just give an energy goal, so we had to determine it. We do think that this is a pretty robust goal. I'll explain why as we go throughout. So, it could be used for other parking structures that are primarily lighting in a variety of climates. But in case, there are parking garages in extreme climates or are very different use cases where you might have to determine your own. So this is how we did it. The first step is to look at the occupant and task type. So, who are you building the garage for? We're only using energy because there are people using this garage. And this is going to be NREL employees. And so we started out really by doing a survey of our campus and figuring out what lighting requirements were typical for our employees to see. And we also used resources like the IAS NA Lighting Handbook, the 9th edition, and the CBEA High Efficiency Parking Structure Specification, the version 1.0. There is a newer version, but at the time of developing our goal, these were the resources we were using. And we decided that, okay, we provide 1-foot candle minimum throughout the garage as our base level of lighting. And we're focusing on lighting here because that's the main energy used in the garage. Because we did not include, we assumed it would be above ground, and we sort of forced out through the energy goal any any ventilation requirements. So, as you see in the table here, there are some higher requirements like the entrance during the day. IES will say, okay, you should have 50-foot candles. Well, we just said we want 1-foot candle everywhere because we knew that we were going to use daylighting, and that 50-foot candle requirement is really there to help people transition from a daylit exterior to a dark interior. And since we're having a well daylit garage, we didn't feel that we needed that requirement. And all of our campus environment was well below 1-foot candle actually, so this was a higher criterion than we had before. And also, as a side note, this is not energy related, but when you're thinking through the occupant type, you might want to look at other quality aspects, quality language that you want to include in the RFP. So we put information around glare reduction. so that it would be also a comfortable environment, and reference CBA spec bug rating for that. Okay, so we know the occupant type, the lighting criteria, when are occupants going to use the garage. We used our door alarm data to determine, when are people coming and going? Are there even people here throughout the night? There are other ways to get this information. There are light and occupancy loggers that you can put in existing buildings, or different California organizations have some occupancy data that can be used for different building types. We were somewhat conservative here, and we just said, okay, we're really interested in the nighttime energy use. There are people coming and going. Let's say that there's a 25% occupancy rate at night. We also did a quick daylighting simulation. P&L gave us one of their sample parking structure models from their projects and demonstration projects. And we just looked at a sunny day, it's a sunny climate here in Colorado, and said, when can we meet 10-foot candles? What percent of the area can we meet 10-foot candles? So again, we're a little conservative, and it was 25% of the area on a typical day. Okay, so we know the occupant type, we know when they're going to use it, and now we want to say, we know when they're going to use it, and we know when passive means can contribute to the requirement. And now we'll say when electric lighting is needed, how low can we go? What LPD is really needed for that 1-foot candle? And this chart compares some of the different standards out there. Again, the CBA specification, this is the version 1.0. An important thing to see is that we're on the lower end of illuminance, and we're able to achieve that with 0.05 watts per square foot. But we're also able to get a really good uniformity ratio, 4-to-1 uniformity ratio with that low LPD, because you're not having this hot spot in the middle of the drive aisle, which tends to happen when you have higher luminance. And not to say that you can't achieve greater than 5-foot candles or 0.3 watts per square foot with a uniform distribution. These are just typical examples of standard garage templates and the results they achieve. So we said, okay, we know we can use 0.05 watts per square foot in our energy goal calculation. We multiplied those numbers together and then added in energy use for other systems. We knew there'd be some parasitic loads for controls. We do have high security standards on the NREL campus, elevators, and again, we didn't add in any fans for major mechanical ventilation. So once we did that, we had an actual energy goal in units of kBTU per square foot, but we turned it into kBTU per parking space as in step 5 it says, try to drive a preferred solution. So we chose a 8.5 by 19.5 foot square parking space, and that's on the smaller side. It's not really small, but it's a little bit smaller than average. And we said, okay, we want that to be the sort of driver, and we don't want large parking spaces. We don't want games played with area to have more energy room in the energy goal. So that was our sort of normalization. Another aspect of that sort of preferred solution is that we didn't include the electric vehicle charging stations in the energy goal because we wanted as many of those to be provided as possible. So the result was the 175 kBTU per space per year. That's really determining the goal. Steps 6 and 7 are more of feedback parts of the process. So you want to present the goal to the team. As I talked about in the interviews, they can ask questions if there are any concerns. That can be openly discussed, and the answers, like how exactly should we substantiate this, can be determined up front before the design begins. And then you want to require that this is substantiated through simulation and through measurement so that you know you are successful and you can feed this information into future projects. So from NREL's perspective, we put together the RFP, including the energy goal. We put it out there, and what did we get? The results of the structure are 1806 parking spaces, 90 for preferred parking, carpool, van pool, and it was low cost. It's lower per parking space at $14,172 than the typical cost in the Denver area. We achieved net zero energy, which was one of the overarching goals at the beginning of the project. And the energy performance in design, so substantiated through the energy model, was 158 kBtu per space per year. And that's a 90% reduction versus ASHRAE 2007, 90.1 2007 baseline. To see what that looks like, that 90% reduction, you can see on the left there's the baseline load, which is primarily lighting. That's 12 hours of 0.3 watts per square foot with the miscellaneous loads that we have in the building. And then on the right, the chart shows that reduction. The security, the elevator, miscellaneous loads really show as major contributors to energy use. And then the small chart at the bottom just shows, relative to the baseline, the relative size of the reduction. Had we included natural ventilation in our baseline or 24 hours of lighting, which is very typical for garages since we have 24-hour occupancy, the reduction would have been much greater than 90%.
Shanti, I want to point out that these savings do not include any savings around natural ventilation. You're saying that the baseline is assumed up to be naturally ventilated as well as the predicted energy use, and so there are those savings. And part of the garage could have been ventilated, right? There could have been fans exhausting underground levels of the garage, and because of the site, and so and the design that was you'll see has natural ventilation, fully natural ventilated, but that move as a design move for energy savings is not reflected in these savings here.
Right. Thanks for the clarification. So that was really NREL's perspective. Like I said, we put out the RFP and the goal, and this is what the team achieved. But a lot of work went in to figuring out the design solution. I'm sure you want to know exactly what that design solution looks like. So Phil Macey, who was part of the design and construction team for the garage project and other NREL projects, is going to talk through the solution with us.
Thanks, Jennifer. So here's an early rendering of the garage, and from the south, as you might be able to read there, southwest, looking back towards the garage. And what you're looking at is a building that was premised from a very different first move. Parking garages are typically a formula-driven building based around parking stall sizes and a number of cars that are trying to be placed. And certainly those were requirements, but more importantly, when you're trying to reduce energy use, is to look for try to create a form that reduces energy use from the beginning. And what I really mean by that is that you want a building shape that extracts the free energy that's in the climate. So this building shape is set up to allow natural ventilation to happen. As has been mentioned, that was just a presumption of the way the RFP was written. So you knew that you had to find a way to make natural ventilation work. And we knew from our work on two other net zero projects, office buildings for NREL, that lighting energy is a very big consumer, and clearly in a garage it's the biggest consumer. So you needed a form that allowed natural daylight to enter the building. Then you had to apply all the parking requirements that inevitably are essential to a successful garage. But you can see the sequence is very different there. You first want to think about a form that connects to the climate. We did have some benefit. It wouldn't be fair for me to step past the fact that we had the ability to shape this building to do that in the most in any way we would like to as a design build team. And the site did allow us the opportunity to point the building southward. Not every site would have that opportunity, so there were some benefits that the building had from the beginning, or the team had from the beginning. Having said that, those are also big challenges. You can see this building has a lot of perimeter, to get the daylight in, and that means that the exterior skin, whatever you're going to make the exterior out of, has to be managed very carefully so that you don't overspend on the exterior skin. And you still have to do everything else that garages need to do with elevators and stairs. So we had a few breaks. We also had a lot of challenges that come with net zero. Let's take a look at the next image. So here is a component of the building shown there on the right, as the text indicates, second floor east, and then the photo there is kind of the donut hole, if you will, which is the way that daylight comes down into the center of the garage, and even that area needed to be parked. It isn't actually protected as the rest of the garage is, but it does allow daylight into the balance of the garage. We worried as a design team that those spaces might not be preferred by staff. I could tell you, having parked in the garage, they're actually preferred quite a bit. They're the easiest to get in and out of. And so actually, as much as they're not covered, people make decisions for different reasons and than you might think as a design team. And they're just as popular as any, and you can see that, in fact, they're actually shadowed a fair bit of the time just by the building shape. So not so much that we get daylight in, but enough so that cars on the bottom actually get a fair amount of shadow through the day. That 60-foot wide light well and the 60-foot bay depth, that's the parking standards driving the building, and those have to be balanced against everything else you need the building to do. One of the things we knew from our early work was that a 60-foot dimension is just right for daylighting. Provided you do everything else right, 60 feet is about as wide as you can stretch a building without other tricks and get daylight to bounce through the building. It does require a slightly taller floor-to-floor than a garage might normally have. This building's about 12.5 feet floor-to-floor, and a garage would normally be a little shorter than that. So again, you've got to balance that cost model against these performance goals, and you've got to do a lot of things simply and cost effectively to stretch the building vertically. And oh, by the way, you might recall, you read all the goals at the beginning, there was also the requirement that the building not be that tall, that it be as short as possible. So immediately there's a conflict going on in the design team between the lighting design team who wants to open the building up and all of my friends on the construction side of the recipe who are trying to find ways to extract every dollar we can and put it into other places if we possibly can make it happen. The post-tensioned concrete was a good choice for us. You know, a lot of garages are done in precast. It's great material, works well. On balance, it doesn't work so well with daylighting. That T-shaped form of precast concrete isn't so nice with daylighting, creates a lot of shadows up on the ceiling, and makes moving daylight a real challenge. So the post-tensioned approach was good for us. We have a lot of expertise in that building type here in Colorado, so we can get that built cost effectively. I know in some areas of the country that might prove to be a challenge, but it worked well for us here. And the PV ready piece, a little clarification on the building. PV ready, the project was responsible for the steel structure on the upper floor, but not for the PV on it. So the building was designed ready to receive PV in every way possible, but didn't have the contractual and cost requirement to actually put the PV in place. So for anyone in the audience, there's a split here in the cost of the project. Now, having said that, a lot of jurisdictions in the country have rebate programs that make the purchase of PV, particularly handsome projects like this where you buy PV in large quantities, are absolutely textbook perfect for your PV rebate program. It's often the exact kind of project that the program's looking for. A larger but not mammoth project hits their sweet spot very well, and you might find your jurisdiction real interested in a project like this. It also tends to be a real mark of distinction and is a kind of project that they often want to put their name on. Next one. All right, so I'm going to let Jen talk to this because this is Jennifer's expertise in lighting, so I'll step back here.
So this is just an example of some of the substantiation documentation that the IPT reviewed and the team created throughout design. And this is just a bay to the north of the light well on the east side, and they were trying to achieve 1 foot candle at sort of a worst case scenario, which was decided to be a winter afternoon, February 4th at 2 p.m. according to the weather file. And that was really used, that metric was a proxy for energy savings, the lighting energy savings that they thought would come from having a fully daylit building. So the lights would be off at this point. And you can see how the daylight really reduces towards the floor, but you don't really get very low until you meet up with the other bay. And on the mirror side of this, we're open to the north, so we're receiving more daylight. And this was done using radiance, so it was pretty rigorous analysis for a parking structure. It was a unique aspect of this process, but it was required in order to show that we could have the lights off 25% of the time.
So a couple important things to extract from this, that are just sort of rolled into a plan like this. So daylighting analysis, daylighting design is a part of this kind of building. On balance, though, the buildings are often very repetitive, so it's also something that you can achieve cost effectively. At least anyone in the audience think, oh my gosh, there goes my budget. I'm going to pay for acres and acres of daylight design. You're going to pay for some, and you're going to pay for it up front. You don't want to wait to do this. You want that daylighting design team engaged from move one, and you want your daylighting design team to have authority in your team. You don't want them relegated to a sort of they only can talk when spoken to kind of role. They have authority in the design team, and you have to really push for collaboration, and it's a different kind of a relationship. Your structural and parking engineers won't have ever had to, I would imagine, work with daylighting design professionals. So there's a bit of a partnering effort here where you need to sort of break down walls that folks won't even realize exist between them as individuals. They've just never worked together, and you need them to engage in a really positive and collaborative way. And there's a whole range of things you can do, and I won't go into those. Rest assured that we had to do a fair amount of work that had nothing to do with designing the building, that was about designing the team, that's about human factors, about how people behave when they work together or misbehave if you don't manage the process right. Lastly, that whole fit between daylight and structural engineering is critical. The columns that you see stitched along the two edges are no accident. They're no caprice. They're 30 feet on center-ish, and that matches exactly to the parking stall size so that parking stalls nest exactly with structure. And believe me, that doesn't just happen accidentally. The structural engineer would have very much liked a slightly smaller bay. It would have made his life easier. We really exercise the structural engineering side of our team deeply. So this is a very dynamic process that requires a lot of upfront coordination. Upfront, I mean, in the very, very first phases of the project, you're going to have architecture, structural engineering, daylight engineering, and your contracting team all engaged, and they all have slightly different perspectives on what the right answer is. And it doesn't matter what anybody's exactly right answer is. What you want is the best answer for the project. This is about optimizing the answer for the project and not for making perfect daylighting and not for making perfect parking or anybody's perfect world. In fact, I regularly told everyone, and almost to the point of frustration sometimes, that when they were all equally unhappy, we had a perfect answer. And I say that lightheartedly. That can be a difficult day at the office to get everyone to understand that their job is to care just as much about lighting design as they do about structure, or the construction side of the team to understand that an answer won't be complete until structure and daylighting are satisfied and that sustainable issues are also satisfied, and that if we can't do it in a cost-controlled manner, I'm going to turn back to those same professionals and say, guys and gals, we don't quite have the right answer. We're going to try again. And that is a much higher bar very early in the project than most folks encounter. So there's a lot rolled into what looks like a very simple building, and on purpose, because you need all those answers to balance.
And this is Shanti. Just hearing that from Phil, I think that's the perfect example of what integrated design is all about. That's when you hear that buzzword integrated design, I think what Phil just explained is the practical application of a project that forced that integrated design to happen. So we'll talk about that a little bit later. But I just want to point that out, that really is applying integrated design principles that have to work in any building, and you see an example here.
Yeah, and so we've flipped to our next slide. So it can be done very cost effectively. It can be done, I would submit, pretty handsomely. This is a view just on the edge of the NREL campus. If we were to back this camera up, this would be a sight line from a greater distance that the neighborhood might see. And you can see the building stepping up the hill there. The research support facility, which is an office building there in the distant background, is the other net zero project that we worked on the NREL campus. So structural engineering and parking engineering are deeply meshed here to allow no shear walls to interrupt the building. I won't go into the detail of that, but for anyone who's a structural engineer or understands garages, you know that you may realize, or the next time you're in a garage, you may notice upon this pointing out that there's typically big, massive walls that subdivide a garage because they're the easiest way to take out the shear in the building. We had to get a lot more inventive and still stay cost controlled to take the shear out in a very long building, which can be a bit of a challenge. The upturned beam note that you see there, typically beams would turn down. That would be the typical structural engineering answer. The problem is, of course, then that would reduce the aperture on the south side or at any sun entry point and effectively reduce the amount of daylight. You're choking down that resource that you really must have, and you want to make it possible for it to enter the building really easily. On balance, from a structural perspective, there's not a tremendous difference, although there are some important details in the structure of in creation of the structure that allow you to turn that same beam vertically and support the load in the opposite direction. It changes your structural sequence. It definitely changes the detailing of the actual bar design inside the beam. So there's a series of dominoes that drop. But if you keep the building very regular, and I think you can see in this image, this is a very, very rigorously a regular building, exceptionally disciplined here in its architecture. You can control the cost. Glass stair enclosures, wow, why would they possibly do that? Well, number one, we wanted a building that would actually be attractive and be something that people would want to use. The last thing we wanted to do was to create a garage that would actually induce people to misbehave and try to force their cars into what few surface lots are left. Number one. Number two, energy expectations told us that we didn't want stairs that were going to need to have the lights on all day long. And then lastly, we didn't really want to have stairs that we were going to have to air condition or ventilate. And so having them naturally daylit took care of the lighting energy. The nature of how they're actually enclosed, they aren't actually weather isolated, so we actually allow a minimum amount of ventilation to flow around the glass, and that ventilates that space and actually creates kind of a natural chimney effect so that the heat rises and exits at the top. It does make some really beautiful stairs that folks enjoy using. And the PV on the south facade, we're very grateful that DOE elected to make that choice. That wasn't something that we as the design build team could deliver as a part of the project, but I think DOE as an engaged and intelligent owner made the decision as ownership to add PV to the south facade. It bumps up the energy performance of the garage pretty handsomely and is a really nice architectural grace note. Up there on the roof, the reason that you see guardrail up there, that is a full rooftop PV array is being installed up there. I don't know if the installation is quite complete just yet. Is intended. And is it in place? Jennifer's telling me it is in place. But the important thing to see here is super discipline. So this is architecture and structural engineering working very carefully together with daylight to get the daylight, the sustainability, the price point, and to create something that still has some architectural character to it without being too severe. It's also fairly easy to manage. It actually is in two separate pieces that staff can enter from two different directions, which plays out the parking load on the campus. So it's also a good neighbor in the sense that the building doesn't induce a high volume of traffic through just one entry on the site, and also plays out the exiting traffic later in the day in a good way. Eventually on the south side, we'd have to zoom in a bit, but there's a string of trees that will march along that south side road that you see. So eventually this forms the southern edge of the campus, so that you'll come into campus, park here, and then the campus is a pedestrian-oriented campus, and that's why the garage has been taken to the southern extreme of the campus. Let's take a look at our next slide. So here we are in the center light well, and this is just natural daylight. There's no lights on here. This is a normal Colorado day with light coming down through the center, bringing light to those center parking spaces. Those happen to be the locations for the preferred parking. So if you happen to be someone who drives a rechargeable car, you get the really cool space right in the center. You can come in, park, hook up the charger to your car, and zip right out of the garage out to campus from here. There's a very nice kind of a grand stair, if you will, that makes moving up and down through the middle of the garage a real point of arrival. And that was a real point of concern for us as a design team, to make the garage, to find a way to finesse the necessities of the garage, things like a stair, into a position where the application of them would make for a better experience and actually make this the front door of the campus, which essentially it will be for most folks. It won't be possible for you to go practically anywhere else on campus in the near future. There's a few surface lots, but they'll go away in the near future. You can also see some other important details relative to both cost control and daylight. We used a cable rail at the edges where daylight comes in, and so it's very minimum, almost no impact to daylight. Also very safe, very cost-effective application. It's a hot dip galvanized wire rope, so also stands up to the climate real well. Doesn't require any care or attention. Once you put it there, you don't need to do anything. And in fact, that was one of the requirements in the RFP, was for minimum maintenance as a inherent character of the building. So you'll see very smooth finished concrete and hot dipped galvanized metal as the primary materials. There's just a few places like handrails are painted, but in majority share, the building is intended to be as close to zero maintenance as can possibly be created. And here's those elevations that I noted. We were challenged to stretch the building out the way we needed to get the daylight in, and then still keep the skin as inexpensive or cost-effective, maybe better said, as we possibly could. So what you're seeing here, the upper picture is the rendering, and the lower picture is a photograph of the perforated metal. We learned some interesting things about perforated metal. It is a white perforated metal, but in fact the way it behaves in real life is much more like a light gray. Essentially what we found is that the material behind and around perforated metal really changes its color. If you walk up to the building, that is a white perforated metal, and when you stand back like the photograph shows, it's gray. I think if we had our druthers, we might have chosen a color if we knew it was going to turn gray like the concrete. It's not bad. It's just one of those things that all the modeling in the world sometimes doesn't necessarily tell you how a building is going to behave in real life.
This is Shanti. I do want to point out, though, that that if it was just architectural element and color was the primary importance rather than the level of perforation and what it did to the daylighting performance, then and you didn't have an energy performance requirement, it may have looked significantly different and hampered, in fact, the daylighting performance by trying to enhance the architectural statement of the facade. And so, to me, what's really innovative and unique about this is that because there's an energy performance requirement, that architectural element had to be balanced with energy performance and daylighting, while at the same time still being as beautiful as possible.
Yeah. So we use perf metal. I know in some climates, for folks on the call, you might not use perf metal in your climate. There are architectural exterior fabrics that we looked at that might be the preferred choice in other climates, and maybe with maybe other goals in mind. Integrating with other aesthetics might change some of your choices. Okay, so here you are in the garage itself, fairly light colored concrete. There's that 40% openness factor. Why 40? Well, 40 is kind of the sweet spot. It doesn't really affect daylighting. It also makes the building code guys happy, so that you're still achieving natural ventilation.
And so I'm just wanting to add that the radiance model, the substantiation model I showed earlier, was just the result of many iterations that worked on or that looked at different openness factors, different widths, different positioning. So it was a determined result. Yeah,
no accident there. You also get some sense of that the vertical, that roof is up higher than dead minimum by all means. And you may or may not be able to perceive, depending on the scale that you're seeing this image, but the roof has a kind of a sawtooth pattern to it. And you may have noticed that in the first image. And that sawtooth is, again, something that's not just because it's cool. There's a 10-degree slope on the roof. And why 10 degrees? Well, 10 degrees is the optimum angle to get the most amount of sunlight without trying to get the perfect amount of sunlight. What do I mean by that? In this latitude, you would need to tip the solar panel to 42 degrees, a very steep angle, to get to 100% solar capture. On the other hand, if you back it down to 10 degrees, you get 90% of the solar capture. And the PV industry has determined that that's an angle that they feel very comfortable with. So we went with that angle. We also used that in our work on the RSF buildings. They have a similar slope to their roofs. And so the 10-degree slope works well for PV solar absorption, and it's not some NREL concocted or design build team concocted answer. It's one that the PV industry, as an industry, has accepted. So you've got essentially a consensus answer. So should you choose to put PV on a building, you might well want to consider a 10-degree angle. Sheds water very nicely, isn't too tall, and you get very good solar capture as well. Okay, and then if you're on the other floors, besides the top floor, this is the view you'd see. Flat slab, real simple beams. We worked hard to get the mix to be lighter without doing anything special to it. Again, we didn't have the dollars to go and buy a tinted mix by any means. But if you work with your concrete provider, where they get the aggregate and exactly whose paste they use to make the concrete are all variables you can control. You don't often ask to control those variables, and so they send you whatever mix they want to make. But if you're building something the scale of a garage, they're more than ready to have that dialogue with you. If that would make the sale more attractive to you, that's the dialogue they'd like to have. So we fiddled around with exactly whose concrete paste, cement paste we were going to use and where exactly the aggregate was going to come from. And, the few variables that you can control with concrete all do have some effect on the color of the mix. The next trick, of course, is now being excruciatingly, brutally rigorous with your quality program. And believe me, we sent back whole full trucks of concrete because they weren't the right mix. And that does not make your concrete mix subcontractor happy at all. But if you've written your contract with them correctly and you've made it absolutely crystal clear what your expectations are, and they're a part of the contract that you've executed with them, then when that truck leaves your yard and you haven't taken anything but a slump test and a color off of it, well, that's just an unfortunate day, and you'll probably have some follow-up meetings to talk about that. But that's how we got a very consistent color across the garage without paying more for it. Again, you know, sustainability has become enough of an issue that these kind of issues aren't outliers. They're things that your concrete provider has heard from other people. And again, if you're building something the scale of a parking garage, it's something that they're ready to work with you on. Those are about as big as long a spans as you can make and still keep the slab completely flat and not have to put any intermediates in it. It only becomes cost effective if you're very careful and make a very regular structure. So there's a lot of discipline that's applied across the whole team, and we work very carefully with our rebar detailers to make sure that all the decisions, even the smallest decisions, how much of a loop do you make at the end of the bar, how often do we have to make the loops, all those decisions all the way down to that level were looked at carefully because of the multiplier. You know, a decision like the length of a loop that multiplies quite literally maybe 10,000 times in a building of this scale, if that loop is 2 inches shorter, that's 20,000 inches. That's a lot of steel that somebody just shrugged and said, oh, well, I always draw the loops that long. Why? Well, we just always do it. Well, don't do it then. I mean, I say that lightheartedly, but you do have to kind of get engaged with the detail to that level because there's a lot of automatics that happen in a building, particularly something very recipe-driven like a garage, that you want to look carefully at and make sure you're not doing anything that you don't have to do. By no means am I suggesting that we bent any rules to the breaking point. We simply played smart with every single rule we had to touch so that we didn't do anything extra that didn't have benefit. And then we could go and put the money someplace more effectively, like doing nice glass stairs or doing the grand stair in the middle that, oh, by the way, has a skylight over it. The only way there was money in the job to do that was to be real careful and task everybody on the team, all the way down to our subcontractors, with the effort to not wait until after the price was too high to then do value engineering. We tried to build the value all the way through from the beginning. That largely was driven by the contract that didn't have any adjustment in price. We knew we were never going to get another dollar for the job. So fixing the price and then adjusting how much you get for the price is a really smart move as ownership. So here's some nice interior shots. I would suggest nice for garage. You know, a pleasant place to come into work every day, even in harsher weather, a pleasant place to be. That center stair is protected and pretty wind sheltered. We get some pretty strong winds in this part of Colorado. And then the exit out there to the bus actually is protected, so on those snowy days or windy days or a combination of both, you've got a pleasant place to stay. And it's not something that the maintenance team has to do heavy lifting on all the time.
So I think Phil did a great job of really showing all the thought that went into the design up front, very driven by the structure and materials to address the goals, the energy goals, and all the other goals of the project. So when systems were added in, there was a lot of consideration as well, but you know, really we just needed to add the electric lighting. And I say add here, all of this was considered in tandem to the structural decisions, but the actual specification for the lighting fixture was made. As I said, we had a lot of security equipment and miscellaneous loads. Everyone would have fire alarm controls, but we do have gates that we can close at nighttime for entrance into the garage, emergency phones, and security cameras. Those are loads that you may or may not have in your building, and that's why the 75 kV2 per parking space goal can still work for different structures that have different needs. If you have higher lighting requirements, you may not have the same security requirements. a lot of thought went into the gate, the specific type of gate that was specified in terms of ease of use and energy savings. We use traction elevators. They're not regenerative, but they are traction, which is about 50% energy savings over hydraulic. There are LED fixtures in the elevators that turn off when the elevators are closed. And you can see the picture here. We have a parking management system, top right, and the bottom right are the electric vehicle charging stations. The parking management system was one of the lower tier goals, and the team did give it to us. And that is useful for closing off floors. We can close off entire parts of the garage to encourage people to park in a more condensed area so that lighting use is less or maintenance can take place on different areas. The 60-foot structural bay was primarily driven by daylighting, but there was consideration towards electric lighting in this decision because for typical parking structures, there would be 2 fixtures along that 60-foot dimension. Well, with a single LED fixture, we were able to have just 1 fixture per bay, which helped us achieve the 0.05 watts per square foot and maintain the 1 foot candle minimum. This could be achieved with fluorescent as well. We looked at this when we did the energy goal because we really did want it to be a performance specification, and we didn't really want to require any specific technology necessarily. There are also occupancy sensors and photocells. The final specification was the N-Light lighting control system by Acuity, and that's damp location rated, and it's not a photocell or an occupancy sensor per fixture. They just sit in different zones throughout the garage, so there are about 3 to 4 fixtures on each photocell and occupancy sensor. There's also a photocell, one global photocell that acts as sort of an override that we can use because we found that the local photocells did cause some problems because they would be looking at oil spots or something that wouldn't quite give it the range of light it needed to turn off the lights during the day. So we rely now more heavily on the global photocell. And this is a 71-watt LED beta fixture. So here, like the daylighting, the electric lighting was substantiated as well. Same parking day that I talked about before. You can see that it said 1 foot candle minimum, but we are dropping a little bit below 1 foot candle at the edges. Those are very close to the perimeter, and they receive night light, some sky night light. And this calculation is done at L70. So for us, for this fixture, it's I think over 90,000 hours when it'll reach 70% output. And since we have the lights off so much, that'll be many, many years down the road, over 30 or 40 years. So although this calculation shows a little bit less than 1 foot candle, we accepted this as a substantiation document.
Jen will be retired by the time that happens.
Let's hope. Okay, so to show the sequence of operations, how you actually move through the garage, we have a video, and we'll post that when we post this presentation, but for now we'll just show sort of a sequence of images. And so this is early in the morning, before sunrise. A car comes in. You can see the bottom level lights turn on. Okay, a little bit later, car's driving up the ramp. The lower level lights turn off. That set point is adjustable, very easily adjustable for the control system we have. It's set to 2 minutes. The car goes up the ramp, and again, as it keeps, you can see the brake lights, and as they're moving up, the lights are turning off. And then this is early in the morning. This is about 6 a.m. You can see the lights are still on. There's activity going on, but we haven't quite reached, the 1 foot candle or the set point in the areas that we're showing here. Sun is rising, and then at about little after 7 a.m., maybe a little closer to 8 a.m., the lights shut off for the day, and this is pretty standard. So you can see people are moving, the occupancy sensors are picking up motion, but the lights aren't turning on because the photocell is overriding those. And continues throughout the day as the garage fills up. So we have a little bit of meter data to share right now. It's preliminary. We haven't had a lot of time to do validation or checks. But so far, we're using, in the summer months, we're using about 107 kBtu per space per year. So that's versus the 175 kBtu per space per year goal. That will increase certainly over the year because we'll have less daylight, shorter days. The colder weather will result in heat trace, camera heaters, and more elevator shaft heating use. So, we're very low compared to the goal now, but it will go up. But our expectations are being met. The sequence of operations is working as it was defined early in design. And so just to show the load breakout again, you've seen the left image already. That was the predicted energy use at the 90% reduction. And the right image is the actual use. So, we're using, because it's summer months, we're using a little bit less lighting than predicted. Miscellaneous loads are a little bit higher. And so it's not a perfect breakout either of the submeters versus what was grouped in the energy model. But it's pretty close. And over a 2-week period in July, you can see this end-use breakout again. The miscellaneous loads, lighting and elevator are security and elevator are fairly consistent at about 2 kilowatts, a little bit higher. And the lighting is fairly erratic because of all the controls. But it's still very, very low. I think I wrote down it could go up to about 90 kilowatts if everything were on. So here is same period of time in July, the lighting in blue, the lighting load in blue, and then an overlay of solar resource, just to confirm that the lights are going off, according to the expected daily contribution. So for Tuesday through Friday, you can see around, a little before 8 a.m., solar resource gets to about 50 kilowatts, and the lights go off. There's still the use of the garage is going up, but the occupant use is going up, but the lighting energy use goes down. But on Monday, it was a very cloudy day, and so it took until noon or so to actually have the solar resource to shut the lights off. So that's probably a profile that we'll see in the winter more often.
So a couple summary slides here. I think you've heard me chime in as I see innovation, things that are different about this process, and so I wanted to highlight some of those here. I think there's a lot of innovation that we talked about in the way that the procurement or the acquisition of our design build services are put together using what we call this energy performance-based design build process. To me, as a champion that's fought for energy efficiency in various projects over the course of my career, haven't been ever successful as I've wanted to be. When I can put it into a contract and require a certain level of energy efficiency, it makes the job of the energy champion so much easier. And that's because it becomes a requirement, and that everything you heard Phil talk about with the integrated team and being able to make decisions in context with an energy goal is what we've always wanted. And so when in my experience, when that can happen, that's when energy efficiency can be integrated and be cost effective. And that all the energy model and the cost model balance, when that happens, that's really what we hope for. So any process that can allow that to unfold, I think there's a lot of innovation there. And so we're seeing that in various projects on our campus as well as throughout the industry that's starting to go to more performance-based design build types of contracts. And so on the design side, I think because of this innovation on the procurement, there's a lot of innovation in the design that had to happen for the team to be able to meet the goals and meet the budget that was given to them. I love the stories about how the structure is balanced with the lighting and the daylighting design. I've never heard of a parking garage structure ever consider things like what bays should what size of bays should be designed so that we can install one fixture per bay, get the lighting power density down to what we need to get, right? And so that type of insight and informing of structural design from the energy champions in the team so that it can be done right is, I think, a great innovation in the design process and the design strategy. That's that second bullet there about resulting in a low lighting power density with good nighttime cutoff, because that was a key consideration early on in how the structure was designed. And an innovation in being able to provide a beautiful, Phil called it, Hans might call it beautiful garage is especially in the stairwells, and being able to use that central stair to get in and out. It's easier and more beautiful to use, and elevators are damp and hard to use. You got to wait for the elevator to get you up 2 or 3 flights. No one ever uses the elevators. We'll see. In the winter that might go up a little bit, but in general the elevators just sit there, hopefully with the lights off. And so those are some great innovation being applied to a garage that we've seen. And so for me, it's I think the result of this innovation is a cost competitive and energy efficient, world-class energy efficiency, beautiful garage that is the front door to NREL. This is what you see when you drive by on the highway on our campus, and so it is a facility that's kind of the ambassador to NREL from both the local community as well as the front range of Colorado that drive by it every day on the main highway. So that's some of how I see the innovation happening. So we've got a fair amount of resources out there about, in general, what was this energy performance-based design build process, how it's applied to office buildings, to cafeterias, to the smart grid research laboratories, to supercomputers and data centers, and the parking garage. So it's different depending on the facility type, but we have a how-to guide being developed this year. So look for that on the end of this year. The RSF, the Research Support Facility, has a whole host of publications available, including how to incorporate energy use requirements into an office building RFP, available at nrel.gov/RSF. And Jen's been working on an overview of the parking garage, expected shortly here. We'll be updated. These slides will be updated with that when it's available, as well as the CBA parking structure lighting spec. There's a latest and greatest one available. We'll hear about in a minute, and then as well as the LEAP campaign. So this is the opportunity for Linda to kind of we have Linda Sandal and from P&L that is running this campaign, and an opportunity for her to fill us in on that. And so, Linda, you're available there?
I'm here.
Great.
Great, thanks. Wanted to just mention a couple of things on the list in terms of the resources. First was the high-efficiency parking structure lighting spec, and there's a link on the page here where you can find that, and it's something that was developed by the Commercial Building Energy Alliances, and it allows for LED, fluorescent, and induction technologies. And by applying the spec, you can expect to achieve 40% or more energy savings, and as you've seen with the NREL presentation, adding in controls and daylighting will certainly get you a lot further than that. There's also a spec for parking lot. You go to the site and can pull that up as well. And also the lighting energy efficiency in parking campaign, that last bullet there. This is a new effort that's designed to increase the uptake of high-efficiency lighting in parking lots and parking garages. And the effort really grew out of the CBEA lighting project team and a desire to increase use of the resources that we developed, including the parking structure spec. The LEAP campaign is a partnership with the Green Parking Council, the International Facility Management Association, and the Building Owners and Managers Association. And these partners will be providing really the outreach and the recognition parts of the campaign, and PNNL will be providing technical support. And the goals are again, really just to increase a number of parking lots and parking structures that deliver attractive lighting while saving significant energy and money. We'll also be documenting best practices and results of the energy savings, and you'll see when we launch this that the NREL parking structure will be something that we reference. We'll be recognizing successes. The partners will be coming up with categories for recognizing success and for things like highest energy savings, most sites designed or renovated. We'll also be helping businesses develop a business case for high efficiency exterior lighting and providing resources for that. And timing for the campaign, this fall we'll be launching it probably the September timeframe. So we're in the process of working on the website now and just defining all the details. So you'll be hearing more on that soon. And that's all I've got.
So great. So thanks all for your time, and then we've got we went I think a little longer, but we've got still some time here for questions that I believe some came through over the net meeting here, and so we'll be Michelle will read them to us and direct to the appropriate speaker so we can attempt to address as many questions as we can in the next 10 minutes.
Absolutely, and if you have additional questions, please go ahead and submit them via the Q&A pane at the top of your screen now. And we will go ahead and get started. Paul Wessel has a question toward the beginning. How did you figure out what the fixed price was? And I think this was within the first couple of slides. So I don't know if you want to try to take it from there or if we need more elaboration on that particular question.
That's outside of our pay grade, I think, in terms of the dollars that are provided. There's a whole congressional allocation to the Department of Energy and the national labs for a project, and so budgets and funding are developed through that. Part of our I think part of the way that this process is different is that we're not necessarily upfront committing to a certain size, square footage, or a certain program. We're committing to maximizing that program with the dollars that are available, and so there's a lot of early estimating that happens, I think, to try and determine how much money is needed, but that's pretty high level without necessarily knowing number of floors of garage, how many spots you can actually afford. And so, in general, that's how a lot of our projects are funded, is that we get a chunk of funding for a general program and meet a specified need. And so the need in this case is fit as many on-site parking stalls as possible into the garage. And so the RFP is structured that way, if you remember the performance objectives. But it also has to be balanced with everything else that we're trying to do with a garage. And so all of our projects on our campus have been typically funded that way.
Right. And we have another question, and it was concerning the solar portion. This person wanted to know what the cost was per watt, and then they also had a secondary question that is NREL doing any research on the amount of solar that could be harnessed across the country using PV on parking lots and decks specifically?
So I can take the first one. This is Shanti. Yeah, it was that PV system was procured 2 years ago now, I believe, and so that was a competitive solicitation out to the various PV integrators that are available, and it was roughly around $4 a watt installed. And so that's, and I know that was 2 years ago, and the installed cost of PV has significantly dropped since then. So on those larger scale systems, that's in line with what the industry was paying at that time. That's unsubsidized in terms of federal tax credits or local rebates as well. So, and Jen, I think it looked like she knew the answer to the second part of that.
I actually don't know if there are any specific resources or studies going on about looking at the area, so the possible area. It's very possible that is happening in NREL. But, anecdotally, we just gave a similar, presentation to NASA recently, and we got a lot of responses back that was something they're very interested in. Is just the simple approach of just adding renewables to their existing structures and using a similar procurement method to do that. So.
Yep, I would add that the solution varies depending on your climate in terms of adding a structure over parking. For us, we've got a lot of wind in our site, and so a lot of our structures, the structural requirements for PV over parking are significant because of wind uploading issues. There's also snow loading issues that are less of an issue than the wind for us, but other climates might have additional parking structure design criteria based on their snow loading or not. There's plenty of places without snow loading that result in a lot less structure over a parking garage to hold PV systems because of that. But you'll see lots of different designs that are out there that are available now, depending on your climate and what you're trying to do with this, the shedding of snow off of covered parking, and there's a whole host of climate-specific issues to deal with. But we're seeing it being done in all those climates, slightly different design response, but still technically and cost-effectively being done now.
Great. All right, the next question is contrast during the day with bright sunlight an issue? And there's some follow-up comments here that bright perimeter versus much darker, although still over 1 foot candle in the center areas. And then perhaps she's wondering if the openness of the structure design helps to mitigate those contrasts, and wants to know a bit about how the vertical luminance compares versus the target specification.
Okay, so that's a really good question because it's something I've been noticing a lot lately. There is one location in the garage where I think contrast is a little bit of an issue, and it just happens at a very specific time of day when sunlight enters one of the entry points, and you're turning sort of towards a dark wall. You haven't quite made the full turn towards a view of the open where you see the sky, the open area yet. Where there is a little bit, you have to go a little bit slower. So, that's where that higher luminance could come in. So, future recommendation, feedback to lessons learned is maybe really add time into consideration at those entry points, even though you may not need 50-foot candles as recommended because it is fully daylit. There may be times a day where you want to think about adding, a little bit higher luminance, or maybe just some simple design features like, adding some brighter walls near that area could have solved the problem, some additional paint or something. So it is something, a lesson learned for us. But for the most part, throughout the garage, on a general level, there's not an issue, and your eyes adapt so quickly that, as you're moving through the space, yeah, it looks bright outside or it's bright in the light well, but as soon as you have entered into the space, made it through that transition area, it feels very bright.
So you're saying, Jen, that it would be a problem if it was 1 foot candle everywhere and there was daylighting, but because the daylighting contribution is so high that it's not 1 foot candle, that
it's about, so the horizontal luminance is much closer to 20-foot candles, if not higher, typically, and almost all the areas, and then it really gets down to 1 foot candle at these sort of slightly buried areas, or right where there's a portion right up against the hill. But you've already made it into the garage. You've already sort of been transitioning in this 20-foot candle environment, and you're going down to a 1 foot candle environment. So, yeah, there is. I would say the only concern there, or the lesson learned, is to pay special attention to the entry points when direct sun does hit those areas. And the vertical luminance, the measurements I've taken have been well over a foot candle at nighttime, so I haven't taken them in every location, but they are meeting the specification and the IAS recommendations.
All right, and then this is our last question in the meeting, so if you have any additional ones, I think we're pretty much out of time after this one, but feel free to submit them in here and we can try to follow up with you directly. The last question is, who owns the PV output, and did you use a PPA?
So the specific PV system on the garage we've got is not a PPA. We have other PPAs on our campus on the roof of RSF, for example, or other standalone PV systems on our Mesa top. This specific system was a recovery-funded PV system, and so it is Department of Energy owned, funded through Recovery Act a few years ago. So that's kind of where how the ownership of that works. And so, as Phil said, there's absolutely opportunity for power purchase agreement system on parking garages, and it would be a perfect place for those that are in the business of owning and financing and integrating renewable systems for other owners to consider investigating what we would have done if recovery hadn't necessarily provided us the opportunity to own it outright.
Okay, great. I think that puts us pretty much at our limit of time, so I'd like to thank everybody for joining us today. If you have additional follow-up questions, you can email the folks here on this slide. You can also submit those on the Q&A panel. We'll have it open just for a little while longer to collect stuff offline. Thanks again for your time, and this concludes our meeting.
Thank you. This does conclude today's conference. Thank you for participating. You may disconnect at this time.